Okay, so I said yesterday that this second chapter is about things involving intersections, right? So today, yesterday what we looked at is like the biggest collection of sets where every pair of sets intersects on a non-empty set. This time, what we're looking at is something a bit weirder. Actually, maybe it's not that weird. The stuff we're gonna do next week is weird, but we're going to look at things called sunflowers. So a sunflower with p petals is a collection F1. So it's a collection of p sets, F1 up to Fp, such that all of the intersections are the same. Meaning if I take Fi intersect Fj, it's equal to Fi prime intersect Fj prime for all distinct I and j and I prime and j prime. Okay, so if I take F1 and F2, I look at the intersection, or I take F1 and F10, or I take F13 and F6, and I look at their intersections, all of those intersections are the same. In the literature, sometimes you'll see the word delta system, but we're going to call them sunflowers because that's funner, isn't it? That's a nicer way to talk about them. This is my crappy drawing of a sunflower here. Is the definition clear? Okay. Yeah. But like the general construction we had where they all contain that, it was all sets containing that point, that would be problematic. But except in the case like where the uniformity, the size was 2, where we had set, yeah. But if you had sets of size 3 containing all the ones containing 1, that would be a problem. But if you had a bunch of sets of size 3 that don't touch each other in any other way, they're just like this, that would be an example. So, okay, so this is a sunflower. Why is it called a sunflower? Well, because it kind of looks like this, right? If you take, it's a bunch of sets where they all have a kind of common core let's call it S. So let's say if I have a sunflower, we call the common intersection S, or sorry, we call it the core. So it's a collection of sets that is a sunflower if there's a set S such that Fi intersect Fj equals S for all I not equal to j. Yeah. So this is what it looks like, right? There's a central set that everybody has. Every S is a subset of all the sets in the collection. And then the part that's not in S is hanging off here. And all of these ones are disjoint, right? There's no common element of these two things because otherwise it wouldn't be a sunflower. Okay, so this is the reason it's called a sunflower. It kind of looks like a flower. So what we're going to try to do today is find sunflowers in a collection. So the question is, how big does a collection have to be in order to guarantee that you can find a sunflower with p petals? Or maybe to phrase it slightly differently, kind of off by 1, how large can F be, where F is a collection of sets of size k, if F does not contain a sunflower with p petals. So we've got 2 parameters, right? In some sense, there's a k here and there's a p. So it's some function, or what I want to show is that it's some function of k and p. And note that we're dealing here with a game we're living in like all the natural numbers. We're not, all of this is going to be true if I restrict it, but even in the natural numbers, yeah, it's just nicer to live in a infinite ground set. So all I'm trying to find is one sunflower. So and the core can be of any size. So yeah, I'm never going to say like I want to find a sunflower where the core has size 3. Or if I could add that parameter to the question and say, how big does it have to be to find a sunflower with a certain size of core? But that would be a little bit problematic actually dealing in the in this infinite universe, because you're not going to find that. But yeah, so all I'm looking for is one sunflower with p petals, and the core can be any size that I want. I just have to find it, some kind of core. Does that address the question? Okay, cool. Okay, so how do we find a sunflower, basically, is the question. Here's one thing to point out, though. This problem would be, the answer would be infinity if you think about it, what if I just take a bunch of disjoint sets, right? Disjoint sets of size k. It doesn't really look like this picture of a sunflower, right? But it's still a sunflower. It's just a very sad sunflower where all the petals have been ripped off the core in some sense. The core is empty. So if you have a collection of disjoint sets, that counts as a sunflower. It's just a sunflower where the core is the empty set. Okay, so that's an important thing to remember here. Having an empty core is okay. It's just a sad, ripped apart sunflower. Is that clear? But it's still a sunflower. It satisfies the condition. If I take the intersection of any two sets, it's the empty set. So that's a sunflower. So yeah, this kind of shows that you can't really, if I said I want to find a sunflower with a core of size 3, you can't really find it because I could just take disjoint set. Okay, so this is known as the Sunflower Lemma. I believe I might mess this up, but I think it's Erdős and Rado. So what it says is that for k at least 1, if F is a subset of, it's a collection of sets of size k from the naturals. Of course, the naturals are just convenient, but it doesn't really matter where these sets come from, right? It just has to be, they can come from anywhere. It's a finite collection of sets of size k. If the size of the collection is greater than k factorial p minus 1 to the k, then F contains a sunflower with p petals. So this is just some finite bound which depends on our two parameters. It's finite, but it's pretty big, right? It's got a factorial and an exponential thing in there, but still it's finite. Is the statement of the result clear? Yeah, totally. So, the petals, I guess, always, the way I'm defining petals is like they're the sets in F, so the petals have the same size, but the cores can be different sizes. Yeah, so I'm not claiming anything about how many sunflowers it has or anything. I'm just I am saying that there's at least one sunflower. There could be lots, that would be even better. But yeah, basically, if F is this big, you can't avoid sunflowers. There's always going to be one, is basically what I want to say. There could be lots, though. I think probably if F was this big, there will be lots, but nobody knows how to prove that. But we can prove that there's at least one. Any other questions? Yeah, we'll talk about this bound a little bit later. Okay, so this is just a restatement of it. And what we're going to do is go by induction on K. So K is the size of the sets. K is this thing, right? So K equals 1, I'm kind of okay with. What's the lower bound we get? So if K is 1, we get K factorial, we've got K factorial P minus 1 to the K, which is just 1 times P minus 1. So that just says that F is at least P. If I've got a bunch of collections of size 1, there's P of them. That's a sunflower with P petals because, this is just P disjoint sets. Yes, this is at least P of them. Okay, so that's just the base case, like usual. Well, not always. I mean, in inductive proof, sometimes the base case is the hardest thing. But in the ones we've been seeing, the base case is pretty easy. Is this clear, though? So it's just, you got P sets, they all have size 1. Yeah, the way we're doing this, we're not having repeated sets. So F is a collection of sets, not a multi-set. But yeah, if you adjust the parameters, this would even work with multi-sets. Anyway, let's not get into but yeah, okay, so right. Okay, so K is at least 2 now. We're doing the general case. Now, here's the thing, like, we've got this kind of issue that, as I said, like, if we were looking for a sunflower with a non-empty core, you're not going to find it because the sets could be disjoint. So we sort of need to address this at some point, that you could have just a lot of disjoint sets. So we're going to do that from the beginning. So I take A1, A2, up to AT. I don't know what T is, but it's some number. And I make this as a maximal collection of pairwise disjoint sets. Okay, so I take as many sets as I can with no intersection at all between. Okay, one thing I can say, well, can anyone predict what I'm going to say here? So, yeah. Finally many of the sets in F, or yeah, I guess maybe to make it more general, maybe I should say take a you very well could. The thing is, so actually maybe I'll, okay, first of all, if you had infinitely many, you could just pick P of them and that would be your sunflower. And that's, yeah, so actually I'm kind of assuming there's finitely many, but really, although actually, I mean, really, this whole sunflower lemma, we could just, like, we're only assuming a finite lower bound on F. We could really just assume that F is equal to this number plus 1, because if it's true for every, so and then you can't have infinitely many sets in it. But yeah, that is a subtle point. That's good to point out. Yeah, so kind of related to that, if this T was at least P, or if if there were infinitely many of them, or a large finite number of them, but we'd be done, because we just say, okay, take A1 up to AP, and that's a sunflower. Yeah, it's one of these degenerate sunflowers where they all have empty intersection. So it is a sunflower. It's one of these sad sunflowers. So we assume T is at most P minus 1. Okay. So now we're kind of at a loss, right? Like, what are we going to do? Well, this taking a maximal set of disjoint things is going to be useful, because basically, if you know, now what you know is that every other set in F intersects one of these things. So how are we going to use that? Okay. So I'm going to define a set X, which is the union of the AIs, for I equals 1 to T. Okay. Question, how big is X? Yeah, they are, yep, exactly. And each AI has size K, so yeah, just TK, exactly. But yeah, if I was dealing with more general things where I had different size sets, it would be the sum of the sizes of the AIs. And of course, this is at most P minus 1K. And here's the observation I mentioned before, that every set in F has non-empty intersection with X, including the sets A1 up to AT, because they intersect themselves. But so if I had something in F that didn't intersect X in a non-empty way, right, then I could just increase the AIs, right? So this is by maximality. So by maximality of A1 up to AT. Is that clear? Notice I can't say that like every set intersects A1, or I can't say that every set intersects every AI, but I can say that every set in F intersects at least one of the AI, and so it intersects F. And when I say intersects, I mean non-empty, has a non-empty intersection with. But okay. So we can use the pigeonhole principle. So if I look at, so I'm going to look at each X and X, and I'm going to say how many sets in F contain X. Well, does anyone know what kind of bound I'm going to write here? So without looking in the notes or anything, but my pigeonhole, so every set in F contains at least one thing in X, and I want to say that there's this thing in X contained in a lot of things in F. Okay, this is what I want to write. To finish the sentence, like it's containing at least that many sets in F, but I'm going to also write another inequality. But is that clear? Because basically every set in F contains one thing in X. It might contain more, but it contains at least one. If I count up like the containments, like if I count up for each X and X how many things is it contained in, that's going to add up to at least the size of F, because everything in F contains one of them. And then I'm going to divide that among the sets in X. So by pigeonhole, at least one must be contained in that many. Is that clear? Yeah, so I'm trying to say, suppose I let, for each X in X, suppose I let F of X, sorry, I'm writing in the middle of like a sentence probably, but be the number of, let's say, A and F such that X is in A. So what I'm saying is that like if I sum overall X in X, F of X, that's got to be at least the size of F, because everything in F contains one of the things in X. So, if you add up how many times each thing in X appears, it has to be at least the size of F. So I guess then what I'm saying is, because this is that large, there must exist, so by pigeonhole, there exists X in X such that F of X is at least the size of F over the size of X. So sorry, I'll highlight this. This is the stuff I just wrote. So this is all I'm saying. Okay, now we can use the bound on F, right? F is bigger than K factorial P minus 1 to the K. Also, we can use the bound on X. So X is at most P minus 1 times K. So this is greater than, maybe I'll just write out the whole thing, like without skipping a step, just K times P minus 1, which is, K minus 1 factorial, P minus 1 to the K minus 1. which is pretty conveniently equal to, like, if I did induction on k and I like look at the term, the thing, the lower bound when k is k minus 1, this is like exactly the value that you would get. But now we have to like somehow use the inductive hypothesis to finish things off. But yeah, different a's, yeah, sorry. It can be, yeah, any set in F. So all we've shown is that there's something in X that appears in a lot of sets of F, if that makes sense. It is an element of many things in F. So now we have to use that somehow. So here when I write X, this is the special X that we found. So this X is like the one that appears most often or something in the sets of F. And X is, yeah, like X is an element of this capital X, but it's like the special one that we found on the previous slide. So now I define F prime to be, like, I look at all the things in F that have the element X, and I delete X from it. So this is going to give me a bunch of sets of size k minus 1, right? Because I've taken a thing that had X and I deleted X. So it's a subset of this universe. And by the thing that that we proved in the previous slide, this has at least this many sets. That was just the pigeonhole and then the algebra, and then we got this bound. Yeah. and note that we haven't like changed the number of petals. Like the p didn't change in this to like a p minus 1 or anything. The only thing that changed was k. So yeah, F has a sunflower with p petals. So this is just by the inductive hypothesis. And actually, if you think about it, we're actually done. So maybe I'll try to draw a picture. Right. So we've got this X sitting here. And yeah, if you look at this F prime, we found a sunflower in there, right? So these are sets in F prime, and there's a sunflower with p petals, and they have some sort of core. I don't know what the core is. It could be the empty set. It could have 10 elements. I have no idea. But you have some sort of sunflower. Okay, and these sets are supposed to have the same size, but they don't look like it. But yeah, this is a sunflower in F prime. And suppose I call the core S, because I'm not that inventive. Maybe I should call it C for core, but oh well. Yeah, so what I know is that all the sets in the sunflower have the same intersection. Their intersection is always S. Now if I look at the chorus, so every set in F prime corresponds to a set in F, right? It's a set in F that has the element X. So basically in F, like if I look at, so if I take, let's say A and B in F prime, then I know that A union X and B union X are in F by definition. And if I look at their intersection, like it's the same intersection as A and B, except for it has the element X. So actually, like just by adding X to all those things in the sunflower of F prime, we get a sunflower in F. So yeah, this is what I'm saying here. Adding X into all sets of the sunflower gives us a sunflower in F with p petals. I was trying to look at the chat, but it keeps running away from me. Yeah, that's true, yeah. So yeah, and there's a question in the chat about whether X gets added to the core. Yeah, that's exactly the point. Yeah, X will be a thing that's in the core. Any questions about this? I've got a... Yeah, so that's it's kind of tricky because you got these two parameters floating around, K and P, and you have to kind of keep straight like which one we're doing induction on. So actually, we're only doing induction on K, and what we're saying is, we kind of imagine you fix P, and then you just do induction on K. That's basically why that we have a fixed value of P. Like in the case K equals 1, yeah, and like the bound here, if you think about it, this bound is like the same as the bound in the theorem, except you've changed K to K minus 1, but we didn't change the P. Like the original bound also had a P minus 1, so that's kind of a key thing. Yeah. So what we knew at that point was that every A and F, so again, this is not necessarily one of these special A's, contains at least one X in X. Hopefully you can parse this sentence. So if I was to say summing over all A and F, let's say the number of X in X such that X is in A. So this is something we need to get used to. So because this has come up, I think, in the limb inequality, also in Erdős-Corrado, this idea of kind of changing the order of summation kind of thing, that this is the same as the summing over all x in x of the number of a in f, such that x is in a. And the way you can kind of think of this changing summation is like, imagine you had a matrix. So here on this matrix, I write down the elements of x. So this is x. If I take x1, x2, I don't know how many things are in x, but let's say xm. I have no idea. And here I write the sets of, this is going to get dodgy because but anyway, I write on this thing, I write the sets in f. Right, and you can put a 1, so you put 0 if the x1 is not in, if whatever element is not in whatever set, and put a 1 otherwise, like, so 1 in the kind of xi a position means that xi is in a, and a 0 means that it's not. Basically, if I add up all the ones in this matrix, you can do that in two different ways. You can say, I go over all the x's, and I add up, like I can add up the rows one by one, or I can add up the columns, and you get the same number. So this one is, I guess, adding up the columns, or whatever. Yeah, this is the number of things in the A column of this thing, and this is like adding up rows. But yeah, this is just a thing we need to kind of get used to. And because every A and F contains at least one thing in X, this is at least F, the size of F, because each term is at least one. And so this sum, which is the same, right? These are equal, must be at least F. And so there must be some term of the sum. So there must exist, sum X such that, like, the number thing in the thing is the number thing in the thing. I don't know. Is at least size of F over X. Because if you add up size of X numbers and they add up to F, size of F, one of them had to be at least the ratio of those two things. Yeah. So this is basically, it is counting, kind of double counting in some sense, counting, looking from two different perspectives. From the perspective, like if you want to always kind of imagine this matrix, you can count from one perspective of rows or count from the other columns and you get the same number. I don't know if this makes it any clearer or just worse, but okay, cool. So just a bit more discussion about this. Like, here's one thing. So a lot of the results we've seen so far, maybe not all of them. So not all of them were like perfectly tight. For example, limb is not exactly tight. But a lot of the results we proved, like Sperner's theorem, we got the exact answer, right? Erdős-Corrado, we got the exact answer. Kruskal-Katana, we got the exact answer. Harris-Kleitman inequality, also it's a tight inequality, so it gives like an exact answer. Something different about this to notice is that, like, well, it's not believed that this Sunflower Lemma is tight. In fact, we now know that it's not tight. So this bound, what I mean is that this k factorial, p minus 1 to the k, isn't necessarily that good of a bound. It's a bound, it's a finite bound, so that's what they were, we should be happy about that, but we could ask, how much better can this be? So let's just to think about this. So the thing is that this bound is bad in terms of if k is growing, basically. So if you fix k, like you say k is 20, right? And I let p grow, p is the number of petals, right? K factorial p minus 1 to the k, well, it's a kind of, if k is 20, this is kind of a nasty polynomial because it's got a huge coefficient and the exponent is 20, which in the wild I never really see polynomials of order 20. Maybe you do, I guess, but that's a fast growing polynomial, but it's still a polynomial, right? The bigger issue comes from if you fix p. So suppose I want like 10 petals, so I just fix p and I let k grow, right? And the worst part of this is the factorial. So if k is like 10, here I get 9 to the k. Yeah, well, in some sense, the lower bound of k factorial p minus 1 to the k is because the proof works. This kind of greedy, it's a little bit greedy of an approach, right? If you think about it, it's not that precise of a approach to take these disjoint sets and then use pigeonhole. In terms of intuition, it's just, maybe somebody else can find intuition, but intuitively, actually, all the intuition points to that this is not a very good bound. And yeah, the most kind of the worst part of this is the k factorial, because, whatever p is, if it's fixed, as k gets bigger, this is going to be the worst part of this, right? So k factorial, as we've seen on the assignment, if you've played around with Stirling's approximation, k factorial is kind of like k to the k. Okay, it's not quite k to the k because there's this thing and there's an e, but it's kind of like k to the k. Why did I write 1 minus epsilon here? Anyway, maybe epsilon here. It kind of grows like a, k to the k, whereas this is just exponential. Anyway, this is all to say that it's a very interesting problem, an open problem to improve the Sunflower Lemma. So there's a conjecture which says that, the conjecture is that really the actual answer it should be an exponential. So that for every p, there should exist a constant cp such that whenever f is at least cp to the k, it has a sunflower with p petals. Okay, so there's an assignment question on the second assignment that sort of is in this vein, in the sense of saying that, there's an assignment question to prove that you can't do better than exponential. So, there's a construction that you're supposed to verify. But yeah, the conjecture is that exponential should be the answer, but nobody knows. Although people have improved things, so the current record is something like this. So if f is at least this big for some constant c, then it has a sunflower. So yeah, kind of connecting to that question from the chat, the reason for this k factorial p minus 1 to the k is sort of because the kind of greedy kind of pigeonhole proof works. If there were, it's sort of a good thing that there's no intuition about why that's the right answer, because it's not the right answer. So this is a better bound, and so nobody really understands what is the right answer for finding a sunflower.